All right, for question 9, we've got a situation here where a spring is pulled back a distance delta x, and the K value is stated as K, mass M, and the period T naught. And then they said, okay, now the spring is changed. So this is a different spring, and it's pulled back 2 delta x, so twice as much as before, same mass, and the period has been reduced to T naught over 4, which I rewrote as 1/4 T naught. And they're asking what is the spring constant K for this new spring. The old constant was K, and the new spring is something else. Well, if the period has been reduced, then it must be a stiffer spring, right? It's taking less time to oscillate, so stiffer springs oscillate more quickly, so this must be a larger K value. So it must be more than K. But we can figure this out. So some of you might be a little bit questioning, like, what about delta x? Does that matter? Well, let's take a look. So there is Hooke's law, Fs equals negative Kx, right? Which we could investigate, all right? So we would be solving for K in terms of X in Fs. Well, we are given X, right? We know the relative distances of X, but we don't know any information about Fs. So we would be left with an unknown other than K. So we cannot use this equation to solve for K in terms of the other K value. But on the other hand, let's look at this equation. T equals 2 pi times the square root of M over K. So in this situation, we are given both T values. We're given T naught and T naught over 4, or 1/4 T naught. So we're given these values. We know them. We know that the mass stays constant. So that's constant. And then we're solving for K. So, and 2 pi is just a constant. So because K is the only unknown value, we can use this equation. Whereas in the previous one, we didn't have information about the forces. So when you have constants, you can pretty much ignore them. So we could rewrite this as T is proportional to, and then just eliminate all the constants. With 2 pi is a constant, the mass stays constant. So it's proportional to the square root of 1 over K. And then we can kind of investigate what happens to K if T is changed. So let's solve this for K. So let's take the square of each side. Okay, and then we get T squared is proportional to 1 over K. Okay, and now we could rearrange this equation, multiply each side by K, divide each side by T squared. All right, and now we get K is proportional to 1 over T squared. Okay, so what does that mean? Well, when T doubles, for example, K will be reduced by 1/4. When T triples, K would be reduced by a factor of 1 over 3 squared, which is 1 over 9. So it would be reduced by 1/9. So in other words, when T goes up, K goes down, which is consistent with what we said earlier. Well, how much did T change, right? When we look at the change from the initial to the final, it changed by a factor. The factor was 1/4. Okay, so T changed by a factor of 1/4. So what we can do, this expression, is just replace T with 1/4. So we'd write 1 over 1/4 squared to figure out the factor of change of K. All right, so we'll do a little bit of math. This is equal to 1 over, and then 1/4 squared would be 1/16, right? And then we could, if you wanted to, we could multiply the numerator and denominator by 16, and you would get 16. So this does not mean k is equal to 16. It means the factor of change for k is 16. So k increases by a factor of 16 in this scenario.